Good afternoon. Morning still. Got me excited for tomorrow now. Looking at applications of the determinant today. Of course, this will then finish our study of matrices for a while. The adjoint, or the adjugate, depending on the text. The adjoint is the matrix of cofactors. Notice the cofactors go by column, not by row. Right, so the 1, 2 cofactor is actually the 2, 1 entry in the adjoint. That's fine. We can use the adjoint to find the inverse. The inverse of a non-singular matrix A is 1 over determinant of A times the adjoint of A. Yes.
Is there a way to get a specific determinant that you want, and then get a matrix that you want? Like thinking of the project that was due today. Is there a way that you can get a determinant that you want, and then get a matrix after?
So you're asking, given a determinant,
Yeah.
find a matrix that has a determinant?
Yeah.
Yeah. You could just make a triangular, right? You could make your matrix triangular and then just make sure that the elements along the diagonal, their product is the determinant. And then you can just make up whatever values you want above the diagonal or below the diagonal if you want an upper or lower triangular. That's probably the easiest way to do it. So this is why I never use this method for finding the inverse. Because that's a pain in the ass to find. Especially for larger matrices. So I'm just going to bypass that method in class. That's what homework is for. So you do it on the homework. This, however, is really important. Kramer's rule. Let A be an n by n non-singular matrix. Let B be a vector in Rn. Let A sub I be the matrix obtained by replacing the ith column of A by B. If X is the unique solution of AX equals B, then X sub I is the determinant of A sub I over the determinant of A. And obviously, I is your index, and it'll go from 1 to n. As I said, this is important in the study of differential equations. So you'll definitely be using it in differential equations.
So all the applications of matrices, did that all come before like the major maths, or like did we know what matrices were like as a thing, or did that come later? Like all their properties and stuff.
The properties? No. So that would come after matrices.
Mm-hmm.
Right? So someone came up with the idea of a matrix,
Mm-hmm.
and then we looked at them and we started to notice patterns,
Mm-hmm.
and we go, oh, so this is a property, and then we prove it. So that's always how it works. Properties always come after.
Mm-hmm.
And that's generally what math is. You notice a pattern, and you go, okay, well, I claim that this pattern is always true, and then you prove it. So that's what happened with the properties. In terms of when did matrices come about, that I don't know because I never studied history of math.
Like for this, like, even like in differential, did they know what matrices did before that, or was that just like
For differential
coincidence?
equations,
Was that just like a coincidence, I guess?
that's a good question. Again, I didn't take the history of math, so I don't know which came first. I would assume differential equations came before matrices, because I'm pretty certain calculus came before linear before matrices did. Right, that was Newton in the, what was that, 1700s or 1600s? And differential equations are just calculus. So my assumption would be this came after, which means we redid differential equations once we found matrices. And again, that's also very common. We find a new way of doing it, then we kind of just rewrite the book. So if you actually look at some older calculus books, it's very interesting. A lot of the older calculus books start with series. Chapter 1 is series. That's typically how they did the derivatives back in the day. Like, what's the derivative of sine x? We know it's cosine x now. They didn't know that before. They would write sine x as its series expansion and then differentiate that. Same thing with integration. Until we start to notice patterns. So you can find a really old calculus book. Chapter 1 series. It's a great way to start calculus, isn't it? Calc 1, start with series right away, instead of limits. Alright, so now we're just going to be using primitives for a while. So getting a system like this is also fairly typical, right? It's not in the nice order that you're used to getting. So this is our first time looking at it, at least for Cramer's rule. Let's rewrite the system to be in a more acceptable notation. Yes, let's write it that way. Our x vector would be x, y, z. For notation of Cramer's rule, we could say x is the x of 1, y is the x of 2, and z is the x of 3. Of course, that order doesn't matter, right? You could say your x vector is y, x, z, right? Or y, z, x. That doesn't matter. You just have to set your coefficient matrix in the same kind of way. Let's define our coefficient matrix A. Right, and note, right, the condition for Cramer's rule, the coefficient matrix had to be non-singular. So what do we know about its determinant?
It has to be zero. Well, it has to not equal 0.
Not 0. It has to have a non-zero determinant. Which also guarantees that your solution is unique. So if you set up your coefficient matrix, you get a determinant of 0, Cramer's rule doesn't work. Then you have to fall back on a different method. Also, square. So you have to have the same number of equations as unknowns, otherwise you can't use Cramer's rule. Coefficient matrix, let's do column 1, the x. Column 2, coefficients for y. Column 3, the coefficients for z. And we'll take its determinant. I think for these, yeah, we'll do determinant by hand for these to start. And we'll see how long it takes before I get sick of determinant by hand. 2 by 5, 10 times 3 is 30. Plus -9, right? Plus -6. -5. minus 27, minus 12. Oh, good. Everything's negative except for that 30. That's nice. 9 and 6 is 15. 15 and 5 is 20. 20 and 12 is 32. And 27 is 59. So what's 30 minus 59? No, that can't be right. What did I do wrong? 9 and 6 is 15. 15 and 5 is 20.
10 minus 27.
2.
Yeah, it's 29. Same.
59. Ah, okay. That's not the right problem. But we'll stick with it. So my notes are useless. So we should get what, negative 21?
29.
Negative 29? Yeah. And 59 minus 30. I get it. You're curious, the second one, that was supposed to be a 2z, not a 3z. That's okay. A1. Replace the first column in A with that B. Now we take that determinant. Plus 9 plus negative 16 minus negative 5 minus 9 times 8, 72 minus 6. Fifteen and 9, 24. 24 and 5 is 29. 29 minus 6, 23. 23 minus 16. 13 minus 6, 7. 7 minus 72. Negative 65. A2. Replace the second column in A with B. Take its determinant. Six and 8, 48, plus -3, plus -3, minus 8, minus 9, minus 6. Oh, Jory, look, everything's negative again, except for that first term. -18, -26, -37. So 48 minus 37. No, I'm sorry. It's not 3 6s. Should be -12 minus 8. -20 minus 9 is -29. So it's 48 minus 29. What is it? Sounds right. Arithmetic sucks. That should be right now. And finally, A3. Replace column 3 in A with B. God, I love the copy and paste. Now let's take its determinant. 10 plus -24 plus 6 minus -5 minus 9 minus 32. Ten, 6 is 16, 16 and 5 is 21. 21 minus 24, -3. Minus 9 is -12. Minus 32 is -42. No. 44. So x1 would be the determinant of a1 over a. We said x1 was x. x2, which is our y, determinant of a2 over determinant of a. And x3, our z, determinant of a3 over determinant of a. -65 over -29. (29) is prime. And 65 is certainly not a multiple of 29, so sadly that can't be reduced. A2 is 19. 19 over -29. Determinant of A3 was -44. So that should be our solution.
Other than being useful for differential equations, is this the fastest way?
I was actually just gonna ask that. So let me get his question then.
Why is y negative? Are those not absolute valuable?
No, those are determinants.
Oh, okay.
Right, so if you have a matrix inside quote unquote absolute value bars, that means determinant.
Okay.
So because the determinant of A2 is positive and the determinant of A was negative, that's why it's negative. So my comp sci people, do an algorithm efficiency analysis on Cramer's rule versus one of the other methods, like Gaussian elimination. Because honestly, for programming, I don't know which one is more efficient. By doing it by hand, I would say probably Gaussian elimination is the quickest method. But in terms of efficiency for coding, I don't know. So that'd be a good thing to investigate if you're a comp sci. And if I remember correctly, it's been quite a while. The efficiency is that big O. Who are my comp sci people? You're familiar with big O notation, right?
I'm not.
Oh, you haven't gotten there yet.
I just started reading one.
You have to get back to me then. I think big O is efficiency. It is. Okay, good. I have confirmation. So you'd have to do the big O analysis on it. I don't remember the full analysis. I don't actually remember how to find big O. Because like I said, it's been years since I looked at it. It was in discrete structures when I taught it. It was years ago. But that will give you the efficiency, the most efficient method. So since you're familiar with that, I'll leave that to you over the weekend. Come back on Tuesday and tell me which is more efficient. Cramer's rule or the Gaussian elimination. There's your assignment.
Wouldn't it be Gauss Jordan? Because that would be like.
Oh, I'm sorry, yeah, Gauss Jordan. All three. Right, because again, which is more efficient, Gaussian elimination or Gauss Jordan, in terms of coding? I really don't know. I've never really delved into it. So there's your assignment. And if you don't do it, I'm taking points off your exam. And I was like, I regret nodding.
Can I get extra credit?
No. It's a zero. It's a negative infinity to 0 point possibility. I had an instructor do that once. That was fun. If you got it wrong, you got negative infinity points. That was fun. If you got it right, you only got 1 point. So let's actually do the problem that we're supposed to do. Because it's actually a lot nicer than this one. No, of course you want it to resize on it. Why not? Let's make sure that's actually right this time. Yes, okay. And this will also show how big of a difference one simple coefficient change can make. This time, let's not rewrite it though. Let's leave it in that form and see if we can do it. First, let's write out B, because we're gonna need that. Well, that doesn't change, does it? Still 181. Now the coefficient matrix. How do you want to define your x vector? You want it to be the same x, y, z? So coefficient matrix, first column, coefficients of x. 2, 3, -1. And we have to move that x to the left-hand side for equation 3. Coefficient matrix or coefficient column for y. 3, 5, 2. And coefficient column for z. -1, 2, and 3. So we just did a determinant by hand. Let's do this one using software. Calculator or Wolfram? All right, or again, menu, matrix, and vector, 7, and determinant is option 3. And you know how to create a matrix as well. -22. A1, replace column 1 in A with B.
I think they would all be relatively even, like using a calculator. Like if you think about it, like you're just doing 4 different equations, and then like in terms of like Kramer's rule versus
Efficiency?
yeah.
But remember, with Kramer's rule, you have to store more. You may have to store more variables, which does affect efficiency. So that's why I said I have no idea. let's take that determinant. And here, we can kind of cheat. I just scroll up, highlight that, hit enter, it's copy and paste. Because now I just have to change the first column. Negative 66. Let's, while I'm here, just do the other two as well. So again, I'm just going to scroll, copy and paste that first one. Second column gets replaced with 1 equal 1 now. That determinant is 22. And then A3, replace the third column with 1 equal 1. Negative 44. Now I want to try something. If I paste, that's what I thought. Okay. So I have to recopy. Said that was 22. And that was negative 44. Our solution. Determinant of A1, we said was what?
Negative 66.
Over determinant of A. And then determinant of A2 over determinant of A. And determinant of A3 over determinant of A. Three negative 1, 2. Look at that. Oh, yeah, that would help, huh? Look at that. Simply by changing that 1, 3 to a 2, look how much nicer the solution is. So start by defining what you want x hat to be. Let's just set the standard order x, y, z. What's B?
-1, 3.
I think what I'll do this problem is I'll just write out all the matrices first, and then we'll write out the determinant. What's A?
One, 1, 1.
Go by row.
Yeah. Sorry. 1, -2, -3. 2, 1, 3.
A1. So what gets replaced with what?
The first column is replaced with 5, -1, and 3.
A2.
Second column gets replaced with 5, -1, 3.
And A3.
Did you get to five?
Hmm?
Did you get to five?
Well, that's not A3 yet. How would you find A3? What is it? With those are the 4 matrices you need. Calculate the determinants. Who has a determinant to give me? Which determinant are you gonna give me?
Which one do you want?
Okay, pick one.
A is 5.
Someone different who has a determinant to give me. Which one?
I got, for A, I got -8.
For A?
Yeah.
Let's write that down then. Did you get a determinant of another matrix? Determinant of A120 we have
I got 2.
for,
A1.
let's write that down. I'll bring that slide up once I get all my determinants. Whereas one for A2.
I'm not sure about this one, I got -28.
Someone get something different?
I think -10.
We have a determinant for A3.
15.
Anything different? Let's go by a show of hands. Determinant of A, who got 5? It's not an overwhelming majority. We got -8 then. I guess this was a pure democracy if 5 would be voting. Who honestly thinks this is a democracy though? Smart. It's not a democracy. It is 5. A1, who got 2? Who got 20? Again, that's not overwhelming. That's not a good sign. Should be 20. A2. We got -10. Oh boy, again, not overwhelming. That's not good. And -28. Okay, someone's lying. Someone did tell me -28. Someone's lying to me. That's not good. Should be -10. So just check that you're entering it in your calculator properly. What is our solution vector then?
Or -2, 3.
We all agree? I'll take that as a yes. That is the solution for -2, 3. So Kramer's rule, not too bad. Kind of tedious though. So 4 by 4. This one's fine.
Wait, what question are we on?
I skipped.
No.
Because the ones between us are all 3x3s. I wanted to get to a 4x4.
For a brief moment, I thought that I blocked out, I just missed like a few questions.
I should have said, where were you? We did them already. Let's make x, x1, x2, x3, x4. Stick with that order. What's our b vector?
Negative 32, 14, 11, negative 4.
What is our coefficient matrix?
You want me to go by row or by column?
You decide. Just tell me which one you're going to do.
I wrote, -1, -4, 2, 1, 2, -1, 3, 1, -1, 2, -1, 1, 2, 1, -4.
-4. Repeat that last one for me. 1, 2.
Wait, it's -1, -2, 1, -4.
Good? Take its determinant. And then when someone goes, how'd you do that so quick? You go, well, it was obvious.
I didn't know this was a cast on the house.
It's the best method of proof. Proof by intimidation. To find A1, what are we replacing?
The first column,
And what does it get replaced with?
negative 32, 14, 11, negative 4.
Find its determinant.
Negative 2,113.
Obviously. A2. Second column replaced. What is its determinant?
Negative 3384.
Negative 3384. Determinant of A3.
Negative 1,269.
Taking. And determinant of A4. That would be the solution, right, unsimplified? Does that simplify? How?
5 to 8 is 3, negative 1.
Again, that thankfully does simplify. 5, 8, 3, negative 1. Again, but wasn't necessarily difficult. It was just tedious.
There's a lot of places where you can mess up just a little bit.
And let's add, can't use a calculator. Again, wouldn't be difficult, it's going to be extremely tedious to do 4 4x4 determinants. Especially since you can't use that nice shortcut, so you're going to do cofactor expansion for each of the 4. I'm sorry, each of the 5. Or row operations. And realistically speaking, that's still a very small system.
a different number, like, negative 30, negative 33, 51.
Check your entries.
I can have check my entries, like most of the time, but I don't. Would you like to see it?
I can take a look. See if I can spell it.
Wait, no, give it 2, sorry, I got that right.
It's a sub 2, right? Yeah. That's right. How would you find the determinant? I recommend trying just to clear out all the history and redo it to see if that affects it. But the determinant should definitely be negative 3384. So I have no idea where that 3381 is coming from. 3351. Oh, wait a minute. Yeah, that's supposed to be a negative 4, not a. Alright, so that's my fault. Why was I thinking negative 1? I have no idea why I thought negative 1. My fault, so that should work now. So you place that negative 1 with the negative 4. So challenge yourselves. Shouldn't be difficult to do. Oh, sorry. Here's question 3 right here. For question 3, that should be your solution. Just make sure you can get that using Kramer's rule. And for number 4, should get that as your solution. So again, try that at home and make sure using Kramer's rule you can get those solutions. A comment about all the methods we've looked at, they are only good for linear systems. That would not have been good. I would not have used that as an excuse to miss the quiz. If you have nonlinear systems, none of these methods work, which is always fun. Solving nonlinear systems. No. Abstract algebra, abstract. So it's the study of groups, rings, and fields. I'm going to make the second quiz available, like right now. That will be due on Tuesday. That covers week 4 through week 6. All right, so everything since the first quiz up through today. And you have 2 homeworks up. One due Tuesday, one due Thursday. And I think the third project goes up next week. I don't think it went up yet. We start vector spaces on Tuesday. Have a good weekend.